So hello, chemistry students. So this is Mr. Wells, and this is my first attempt at creating a flipped classroom environment where you guys will be learning about the material at home by watching this video recording me talking about stoichiometry. And then you're going to take what you learned from home this weekend and you're going to bring it to large group on Monday and Tuesday. And then we're going to have a practice sheet that you'll work on in class. That way it provides Miss Pollock and myself some time to work with you one-on-one, because stoichiometry can be a little bit of a challenge. So the big question is, what is stoichiometry? So I have this video attached here. I'm not going to play it in the video because I'll attach the actual slideshow to Google Classroom so you can watch this video. And it does a very good job explaining how stoichiometry relates to cooking. So that for those of you that know how to cook and use ingredient lists a lot, this can make a little bit more sense. So stoichiometry, what is it? Stoichiometry is a way to measure chemicals in a chemical reaction. It tells us how many products we can produce if we have so many reactants, or vice versa. If we have 50 grams of products, it tells us how many reactants we would have needed to be able to produce 50 grams of product. So it's very similar to how to cook measurements in ingredients for a recipe. But the really important thing is we need to be able to use this or stoichiometry with a balanced chemical equation. So this is why it was really important the last couple weeks. We've been working very heavily with balancing these chemical equations. This is why it's important that you guys know how to balance equations so we can do stoichiometry. So keep calm. Stoichiometry is easy. It's all about patterns. We just got to teach you how to follow the pattern so you can do these math problems. So here's kind of a chart here. We have relationships from a balanced chemical equation. So I've already balanced. So when we're looking at relationships from a balanced chemical equation, we'll kind of give you this table. And what we're going to see is I have this balanced chemical equation on the top. So we have 4 moles of iron solid reacting with 3 moles of oxygen gas, or O2, to produce 2 moles of iron oxide solid. So with these tables, we need to identify what elements we have. So the first thing we have is iron, and we can put that in the first cell there. And then we have oxygen. And then finally, our products, we have iron. And we got to remember to include our Roman numerals here, iron 3 oxide. So those are our elements we're working with. So now we got to look at our atoms. So how many atoms are in 4 Fe's? We have 4 atoms. If we are looking at molecules, we have 3 molecules of O2 in this chemical reaction. And then if we look at compounds, we have 2 compounds of iron 3 oxide in our balanced chemical reaction. So now we're going to look at our moles. We're going to identify moles, and you're going to find they're exactly the same as our atoms, our molecules, or our compounds. So we have 4 moles for iron, we have 3 moles for O2, and we have 2 moles for iron 3 oxide. So now we're going to look at the molar masses for our reactants and our molar masses for our products. So if we look at our periodic table, we find that our molar mass for iron is 55.84. And then because we have 4 moles of it, we're going to multiply 55.84 by 4. And we're going to get 223.36 grams of iron. And then we're going to do the same things for oxygen. And oxygen has a molar mass of 15.9. And we need to remember 15.99. And we want to multiply by 2 because we have oxygen gas. And then we have to multiply by 3 because we have 3 moles of oxygen gas. So we're going to multiply 31.98 by 3. and we're going to get 95.94 grams of 3 mole oxygen gas. So then we're going to do our last step. We're going to take iron. We said iron is 55.84. We have 2 irons, so we're going to multiply by 2. And then we're going to add oxygen, which is 15.99. We're going to multiply by 3. And we're going to 159.65. And then we have 2 moles of that. So we got to multiply 159.65 by 2. And we get 319.3 grams. And because we only have one reactant or one product, we can go ahead and dump 319.3 grams in for our products. So the last step we got to do is we got to make sure the mass of our reactants is equal to the mass of our products. So if we take 223.36 moles of iron and we add, or grams of iron, and we add that to 95.94 grams of oxygen and we press equals, we're going to end up finding that we have 3.19.3 grams of reactants, exactly the same as the mass of our products. And that's what we want. So on this next slide, you're going to see that you have a similar table with a different chemical reaction. And you need to fill out this table just like I did on the previous slide. So go ahead, pause this video, give this table a shot. If you're a little bit confused yet, go ahead and back up the video, rewatch my process so that you can do this video on your own. So go ahead and pause now. So what we got is we got our balanced chemical equation. N2 gas plus 3H2 gas produces 2NH3 gas. So like we did before, identify what element or what our element is. So we have nitrogen, we have hydrogen, and then we have nitrogen trihydride because we're dealing with a covalent compound. So trihydride. Okay, now we're going to figure out how many atoms we have. So if I look at my atoms, I have 1 atom of N2, I have 3 molecules of H2, and 2 compounds of NH3. Then we're going to go back and put in moles, exactly like the atoms, exactly like the molecules, 3 moles, looking at our balanced chemical equation, and then we end up with 2 moles in our NH3. So now we just got to grab our calculator, look at our periodic table, and we need to figure out our molar masses for our reactants and our products. So if I look at nitrogen, nitrogen has a molar mass of 14.01, and we have 2 nitrogens, so I need to multiply 14.01 by 2, and we're going to get 28.01 or 02 grams of nitrogen. Hydrogen, we have 1.01 molar mass times 2. So we get 2.02. And then because we have 3 moles of hydrogen gas, we need to multiply 2.02 by 3. And we end up getting a mass of 6.06 grams of H2 in our chemical reaction. And then we just have to do our products. So nitrogen, we said we have 14.01 grams. We need to add them to 1.03 grams of hydrogen times 3 because we got 3 hydrogens and get 17.04. And because we have 2 moles, we need to multiply 17.04 by 2. And we're going to get 34.08 grams. And we can go ahead and write that in below for the mass of our products. So if we add 28.02 up, and we add 28.02 to 6.06, we should find that our mass is exactly the same at 34.08 grams of reactants and mass of our products. So we are good there. keep going here. We move on. So why do I need to be able to get that information from a balanced chemical equation? So the reason why, and we're going to look at a problem here in a second that we'll have you look at, but this looks very similar to the chart, the diagram that we gave you in small group A last week. So if we look here, we have mass in the top left, we have volume, we have particles, and in the center we have moles connecting substance A, which is known, and substance B, which is unknown. So this chart tells you exactly what you need to do to be able to do stoichiometry. So say I started with mass up here in the top left, and I wanted to get to moles and end up at particles of unknown substance B. Excuse me. So if I knew my mass, what I am going to do is I'm going to use my 1 mole or equals my molar mass, or my molar mass of my substance, of substance A, and I am going to convert from mass to moles of substance A. And then once I get to my moles of substance A, I'm going to use my mole ratio, which we're going to talk about what a mole ratio is here in a second. And then we can convert to moles, from moles of substance A to moles of substance B. And then from there, all we need to do is we need to multiply moles of substance A by Avogadro's number, or 6.02 times 10 to the 23rd. And that's going to give us how many particles of substance B we will produce if we have a certain mass of substance A. So it's a pretty easy chart to use. You'll be using this one a lot, and we'll give this one to you. But what would a problem look like when we give it, or need you to use this? So here's a balanced equation. We have 4 aluminum solid reacting with 3 moles of oxygen gas to produce 2 moles of aluminum oxide solid. So this is where we get into mole ratios, converting using moles. So if we want to go from moles, we want to convert from moles of A to moles of substance B, we're going to use this mole ratio. So a ratio between any 2 compounds in a balanced chemical equation. So an example of this. So using our equation, we see that we have 4 moles of aluminum, 4 moles of Al. And let's say I wanted to convert from moles of aluminum to moles of aluminum oxide. I want to figure out how many moles of aluminum oxide I have. My ratio is going to be 4 moles of aluminum. That's what I'm starting with. And then I'm going to look at my aluminum oxide and see that I have 2 moles of aluminum oxide to every 4 moles of aluminum. And just like this, we can get a whole bunch of different mole ratios here. Say we don't want to look at we're not wondering about aluminum oxide or how many moles of aluminum we have. Say we were looking at 3 moles of oxygen. So we have 3 moles of oxygen, and that's what we're starting with, 3O2. And I wanted to convert 2 moles of aluminum. To figure out how many moles of aluminum we have, we'd look at our equation, we'd see that we have 4 moles there. We have 4 moles of Al. We have 3 moles of O2. And this would be our mole ratio, one of our mole ratios that we can get from our balanced equation up here. So we're going to use these mole ratios to actually convert from 1 mole of substance to a different mole of substance, to a different compound completely. So we'll have this question here. So we're going to convert from moles of substance A to moles of substance B. And you're going to notice on these slides that I actually have some links provided for you that give you good videos and information that maybe I didn't provide you in your video if you want another resource. So I got hint here, use mole ratio to convert from one type of mole in substance A to substance B. So let's say we're looking at this balanced equation of 2 magnesium solids plus 1 mole of oxygen gas to produce 2 moles of magnesium oxide solid. So let's say I had 35 moles. We'll do magnesium. So 35 moles of magnesium, and I want to figure out if I'm given 35 moles of magnesium, how many moles of magnesium oxide I can produce. So just like we were doing early last week when we were talking about how to convert moles to particles, particles to moles, how we can go from grams to moles, we need to make sure we follow our units here. So we're starting with moles of magnesium, but I don't want moles of magnesium. I want to find moles of magnesium oxide. This is where I want to end. So I need to use my mole ratio to figure that out. So I don't want to have moles of magnesium anymore. I'm going to cancel them out. So I'm going to look at my balanced chemical equation, and I'm going to find magnesium. And using that balanced equation, I see that I have 2 moles of magnesium Mg to however many moles the balanced equation. It says we have 2. So in this case, it's 2 moles of magnesium oxide. So now, if I have a unit on top, I cancel. Moles of magnesium cancel. Same on the top, same on the bottom, they cancel out, leaving me with moles of magnesium oxide. So that's going to be my units. So moles of MgO are where I'm going to end up. And then I can just go ahead and punch this into my calculator. So if I take 3.5 and I go ahead and I multiply by 2, and then we got to remember to divide by 2, we're going to find that if I have 3 moles of magnesium oxide that I started with, I can produce 3.5 moles of magnesium oxide. So this is how we can use this mole ratio to convert from moles of magnesium to moles of magnesium oxide. And if you do need a little extra help, I included this image here in the bottom left, which kind of talks about how we convert from moles of one substance to moles of another substance. So then we can go ahead, and I've got another pause the video on practice. So we have 2 balanced chemical equations here. I want you to go ahead and convert from moles of mercury oxide solid to moles of oxygen gas for number 1. And then I want you to convert from moles of iron solid to moles of hydrogen gas. So go ahead, pause this video, give it a shot. If you need more resources, just go ahead, pause the video, and rewind and look at my process for the last one. So I went ahead and I paused the video so you guys had a little bit of time to work on balancing or converting from moles to moles here. So if we look at my first question, I want moles. I'm going from moles of mercury oxide solid to moles of oxygen gas. So let's say I had 4 moles of HgO. And I want to convert to my moles of my oxygen. So I am going to multiply, and I don't want to end up at moles of oxygen. So I want my mercury oxide. So I'm going to put that on the bottom so that my units cancel out. And then I'm going to look at my balanced chemical equation, and I'm going to see that I have 2 moles of mercury oxide. And then if I want to convert to moles of O2, I'm going to look at my balanced equation. Oh, there's nothing there. So that's 1. There's 1 mole. So I am going to end up at moles of O2. So my moles of mercury oxide cancel out. Moles of mercury oxide cancels out. I put this in my calculator. 4 times 1 is 4, divided by 2 is 2. So if I ever have 4 moles of mercury oxide, I can go ahead and produce 2 moles of oxygen gas. So then if I look at my second problem here, 3 moles of iron solid plus 4 moles of liquid water produce iron oxide solid plus hydrogen gas. So let's say I had 1.5 moles of, let's see, iron solid, Fe. And I want to convert to moles of hydrogen gas. So just like I set up before, I'm going to use my mole ratio. And I don't want moles of iron anymore. I want to convert to moles of hydrogen gas, so moles of H2. And I'm going to look at my balanced equation, and we see that we have up here that we have 3 moles of iron for every 4 moles of hydrogen gas. So I'm going to plug 4 on top, 4 moles. And I want to end up at moles of hydrogen gas, H2, equals, or no, we don't need that equals. I already had written them in. So moles of H2. And when I plug this into my calculator, 1.5 times 4, and then we divide the whole thing by 3, and we find that I can produce 2 moles of hydrogen gas when I am given 1.5 moles of iron. So again, if you have any more questions about this, just stop the video and come back to it. Go back to one of my other parts of the video so that you can get the information you need. If you have any questions about it, just ask Ms. Pollock and myself on Monday or Tuesday in large group. So what are we going to use this for? So 4 aluminum solid plus 3 oxygen O2 gas to produce 2 aluminum oxide. So here's my question. If I have 79 grams of aluminum, how many grams gas or grams G of aluminum oxide can I produce using the above balanced equation? So using this equation up here, and I'm given 79 grams of aluminum, how many grams of aluminum oxide can I produce? So we are going to go back to using stoichiometry. So we're going to go back and we are going to look at this chart one more time. So once again, it's asking us to start with mass. From mass of substance A, we can convert to moles of substance A. Once we convert to moles of substance A, we can convert to moles of substance B. And then from moles of substance B, we can end at moles or mass of substance B. So we can use this chart with any of these problems that I'm going to ask. So here's that equation again. 4 aluminum solid plus 3 O2 gas produces 2 aluminum oxides. So if I have 79 grams of aluminum, how many grams of aluminum oxide can I produce using the above balanced chemical equation? So we're going to start out by writing what I know. And I know that I have 79 grams of aluminum. And what do I want to know? I want to know how many grams of aluminum oxide I can produce if I have 79 grams of aluminum. So I'm going to start by writing down what I know. So 79 grams of aluminum, 79 grams of Al. Well, how do I convert from grams of Al to moles? So you guys should be able to think back and say, okay, if I have 79 grams of Al, I need to figure out what the molar mass of Al is. So if I go over to my periodic table, and I'm going to see aluminum has a molar mass of 26.98. So that's what I'm going to divide by, 26.98 grams of aluminum. And every time I have 26.98 grams of aluminum, I'm going to have 1 mole of Al, 1 mole of aluminum. So now I've taken that first step from that chart I just showed you. I made that jump from grams to moles of aluminum. So now now that I have moles of aluminum, I need to convert to moles of aluminum oxide. So I need to use my mole ratio. I need to look at my balanced equation and figure out how many moles of aluminum I have for every mole of aluminum oxide I have. So if I look at my balanced equation, I want to convert from moles of Al to moles of Al2O3. So my balanced equation up here, I'm going to find aluminum, and I'm going to find that aluminum has 4 moles of Al for every 2 moles of aluminum oxide. So we're almost there. We want to get to grams of aluminum oxide, so Al2O3. So now we want to convert from moles to grams one more time. So we have moles of Al2O3. And then we need to go back to my periodic table and figure out what my molar mass of aluminum oxide is. So if I look at aluminum on my periodic table, aluminum is 26.98, and I have 2 aluminum, so I need to multiply by 2. And then I'm going to add oxygen, 15.99 times 3, and find that aluminum oxide has a molar mass of 101.93 grams of aluminum. So that's what aluminum 2 oxide, and that's where we want to end up. So this is our stoichiometry problem, the math equation that we set up, and that's the tough part. Now we just need to multiply. So now we have 79 grams of aluminum times 1 times 2 times 101.93. And then I always press the equal sign, and I find that I have 116,104.94. But we're not done yet. We have to divide. So then I'm going to put divide parentheses and 26.98 times 4 times 1 parentheses. So that's all being divided by now. Press equals, and I find that when I have 79 grams of aluminum, that I will produce 149.2 grams of aluminum oxide. Okay, so that is a complete stoichiometry problem where we're converting from grams of substance A to grams of substance B. So we have a few more problems that we're going to work on to make sure that you guys get it. But these resources are all here for you. So if you have any questions, just come ask Ms. Pollock or myself on Monday or Tuesday or anytime next week. If you need any extra resources, on the bottom right, of most of these slides, I've linked a whole bunch of videos that I find will help you along the way. So here we want to convert from moles to grams. So I have a video in the bottom right, just like I said before. So I have NH4NO3 solid produces N2O gas plus 2 moles of liquid or H2O gas, water vapor. So my question is, if I have 5.07 moles of NH4NO3, how many grams of H2O gas can I produce? So if I look at that problem and I want to figure out, like, what do I know? What does the problem tell me? The problem tells me that I have 5.07 moles of NH4NO3. And what do I want to know? I want to know how many grams of H2O gas I can produce if I'm given 5.07 moles of NH4NO3. So that's where I'm going to start. Always start with what you know. So I'm starting at 5.07 moles of H4NO3. Solid. So then I'm going to set up my parentheses. I don't want to end at moles of ammonium nitrate. I want to get to I want to get to moles of water, how much water or H2O gas I produce. So now I'm going to use my mole ratio because I'm already starting at moles, so I can use my mole ratio. So moles of moles NH4 NO3 moles. And then I'm going to convert to moles of water. So moles goes on top. Moles of H2O. And then I'm going to make my jump and look at my periodic table. If I want moles of NH4NO, I'm going to look at here. Nothing's written there, so I'm going to write a 1 mole of NH4NO3. So now I want to figure out how many moles of water I have for every mole of NH4NO3 I have, and I find that using the balanced equation, I have 2 moles of H2O for every 1 mole of NH4NO3. So now I've converted from moles of substance A to moles of substance B, but I don't want to know how many moles of substance B I have. So I want to cancel those out. So I'm going to put 1 mole of H2O on the bottom because I don't want moles of H2O. I want grams of H2O. So then I'm going to put moles on top of grams. And I'm going to figure out how many grams of H2O I have. And that's where I want to end. I want grams of H2O. So if I go to my periodic table, I'm going to figure out what molar mass needs to go in this spot here by this asterisk. So if I look at my my periodic table, I have 2 hydrogens. Hydrogen is a molar mass of 1.01. Multiply by 2 because we have 2 hydrogens. And then we're going to add the molar mass of oxygen, and we only have 1 of those. So we're going to have 15.99. And when I press equals, I find that the molar mass of water is 18.01. And that's what I'm going to plug into my periodic table, or plug into my stoichiometry problem. So now I started at moles. That's what the problem told me. I don't want moles of ammonium nitrate, NH4NO3. I want moles of water. Using my mole ratio, I converted. And then from moles of water, I canceled moles of water out. And then I used grams on top because whenever we have 1 mole of water, we have 18.01 grams. And then we can just go ahead and punch this into your calculator. So 5.07 times 2 times 18.01 and press equals. And we find that we can produce 182.6 grams of H2O. So if I were ever given 5.07 moles of ammonium nitrate, NH4NO3, I can produce 182.6 grams of water from the 5.7 moles of ammonium nitrate. So let's work on a couple more problems, and then you guys will be good for the weekend. So here's our balanced chemical equation, and here's our question. If I have 45 liters of chlorine gas, how many molecules of NaCl can I produce? So I know, based on the question, that I have 45 liters of Cl2. So that's what I'm going to start with, and then I want to know want to find out what I need to get to. And using the problem, I want to know how many molecules of NaCl I can produce. So I'm always going to start by writing down what I know, and I know that I have 45 liters of Cl2 gas. So what's my next step? So if we flip back to the chart I showed you, you're going to see or what you should see, is that you have liters here. Liters is a volume. So if we want to convert from liters and get rid of that volume and convert to moles, we're going to use the number 22.4 liters of Cl2. Because whenever we have 1 mole of gas, Cl2 is a gas, we have 22.4 liters of that gas. So then I can convert or put on top 1 mole of Cl2. So now I've converted from my volume to my moles. Once I have moles of Cl2, I'm going to use my mole ratio from my balanced chemical equation. So moles of Cl2. And then I want to convert to moles of NaCl, sodium chloride or table salt. So now that I have that conversion, I'm going to look at my balanced chemical equation, moles of Cl2. If I look up here, nothing's written there, so I can assume that I have 1 mole of Cl2. And then I want to figure out how many moles of sodium I have, or not moles of sodium, how many moles of sodium chloride I have. So I have 2 moles of sodium chloride for every 1 mole of Cl2. So now we're almost there. Now we just need to convert from moles of NaCl to grams, or not grams, I'm sorry. We want to know how many molecules we have. So MOLEC, molecules of NaCl. So now we got to think about back to Monday of last week, and we were talking about Avogadro's number. So now we're going to use Avogadro's number to convert from 1 moles of NaCl to molecules of NaCl. And Avogadro's number is 6.02 times 10 to the 23rd. There's always 6.02 times 10 to the 23rd molecules, particles, or atoms in 1 mole of a substance. So now we can go ahead and put our equal sign. We've converted from liters to molecules of sodium chloride. So that's my unit I'm going to have. Molecules, MOLEC, NaCl. And now I can just plug it into my calculator. Now with this one, I want to be careful because I am using Avogadro's number, so this could be tricky. We might have a big number. So we're going to have 4.5 liters times 1 mole of Cl2 times 2 moles of NaCl times Avogadro's number, which is 6.02 times 10 to the 23rd power. And then I'm going to press equals. And I get 5.418 times 10 to the 24th. But I can't forget to divide by whatever I have in the bottom. So I'm going to press divide, and then I'm going to punch in 22.4 liters and press equals. And I find that if I have 4.5 liters of Cl2, I can produce 2.42 times 10 to the 23rd molecules of NaCl. So again, if you have any questions, you want some more resources, I have a video linked in the bottom that should help you out. So I will erase all this. Erase all of this. And then we can jump into our last section here. So how's it going? So here's our problem that we're looking at. So we have 2 moles of mercury oxide solid decomposes to produce 2 mercury liquid plus oxygen gas. So the question is, if I have 2.3 grams of mercury oxide solid, how many liters of O2 can I produce? So if you go ahead, you can pause this video for a second and give that a shot. And then once you think you've got it, you can start playing the video again and see where or how you did. So go ahead and take a second and pause. So here's our question. If I have 2.3 grams of mercury oxide, how many liters of oxygen gas can I produce? So what do I know? I know that I have 2.3 grams of mercury oxide, and I want to know how many liters of O2 gas I can make. So I'm going to start by writing down what I know, 2.3 grams of HGO, but I don't want grams of HGO, so I need to get rid of that. I need to convert to moles. So what I need to do is look at my periodic table, and I am going to find that mercury has a molar mass of, one second while I find my periodic table. Mercury has a molar mass, Hg, of 200.59, and we only have one mercury, so then we're going to add it to the molar mass of oxygen, which is 15.99, and we're going to press equals, and we're going to find the molar mass of the compound mercury oxide is 216.58 grams of HGO. And we don't want grams, we want to convert to moles. Like everything, we want to get to moles. So there is 1 mole of HGO in 216.58 grams of mercury oxide. So then, now that we have moles of mercury oxide, we can use our mole ratio. And we want to get rid of moles of HGO, and we want to get to moles of oxygen, O2. So then we're going to go look at my balanced equation, and if we look for mercury oxide, we see that we have 2 moles of mercury oxide, and if we look for O2, we have a 1 mole of oxygen gas to 2 moles of mercury oxide. So now we just need to convert from moles of O2 into liters of O2. And the way we're going to do that is we're going to use the number 22.4 because we're dealing with a volume. We're dealing with a gas. So that is where we want to end. We want to end with liters of O2. So then if we punch this into our calculator, this is the setup stoichiometry problem. So we take 2.3 multiplied by 22.4, and we press equals, we get 51.52, and then we just need to divide 51.52 by 216.58 times 2. Don't forget to put your parentheses in so your calculation comes out right. And when we press equals, we find that we end up producing 0.118 liters of O2 when we put in 2.3 grams of mercury oxide. So that one we're converting from grams to liters. And then we have one more practice problem here, and you guys are good for the weekend. So we have 3 moles of iron solid plus 4 moles of H2O produces iron oxide solid and 4 moles of hydrogen gas. So if I have 7.04 moles of H2O, how many grams of hydrogen gas can be produced? So what do I know? I know that I have 7.4 moles of H2O, and I want to get to grams of H2O or H2 gas. So we're always going to start with writing down what we know. We know that we have 7.04 moles of H2O. So this is an easy problem. We're already at moles. We don't have to convert to moles. So then we can jump right in and do our mole ratio. So we have moles of H2O because we don't want to end at moles of H2O. So we have moles of H2O and we want to convert to moles of H2 or hydrogen gas. So then we're going to go look at our balanced chemical equation, and we're going to find how many moles we have of H2O, and we have 4 moles. So we're going to plug that in for moles of H2O. And then we're going to find H2. We're going to find that we have 4 moles of H2 to every 4 moles of H2O. So then we need to convert. We don't want moles of H2O. We want to get to grams of H2O, or H2, I'm sorry. So we have 1 mole of H2. And then we got to find the molar mass of hydrogen. And hydrogen's molar mass is 1.01. And because we have 2 moles, two hydrogen atoms, hydrogen is diatomic, we need to multiply 1.01 by 2 grams. And we're going to find that we're going to have 2.02 grams of H2. So then we put our equals in. We put grams H2. If we look at our problem, we want to know how many grams of H2. So we've got the right units. Everything else cancels out. We can go ahead and plug in this equation. So we have 7.04 multiplied by 4 multiplied by 2.02. We press equals, and we find that we have 56.8832. Now we need to remember to divide. So we're going to put in parentheses 4 parentheses equals. And we're going to end up getting 14.2 grams of H2 hydrogen gas are produced when we have 7.04 moles of H2O. So that is all we have for stoichiometry today. Large group, Monday, Tuesday, you'll have a practice sheet where you need to work on these types of problems. So if you want another resource, I have this video attached here. It's by Crash Course. They do a pretty good job explaining if you just kind of want another resource that could help you out. So that is all I have. I hope you guys have a good weekend, and we'll see you Monday and Tuesday.